All right, so welcome to another deep dive. And today we're going to be tackling something
Okay.
that, you deal with every day,
Yeah.
but you probably never really even think about it, and that's down.
Oh, wow.
Like, we all know things fall down,
Right.
but why? Like, what?
Down.
Even IS down, really?
Yeah.
And
Yeah.
turns out it might completely overturn how you think about gravity and, like, our place in the universe.
Okay.
And to guide us through this, we've got some awesome insights from a Vsauce video by Michael Stevens.
Right.
So get ready, because this is where things get really interesting.
I love Vsauce.
Yeah.
What fascinates me about this topic is that it's such a perfect example of how, like, our everyday experience can hide incredible complexity. You know, we take down for granted.
Right.
But then when you start peeling back the layers,
Yeah.
it opens up this whole new understanding of the cosmos.
Totally. Yeah, it's like it's one of those things that you learn as a kid and you're like, okay, got it. And then you realize there's just like a whole universe of depth behind it.
Right. Yeah.
So let's just start with the obvious, right?
Okay.
Down is the direction gravity pulls, right?
Yeah.
But even that gets kind of tricky when you think about it.
Absolutely. Just imagine two people standing on opposite sides of the Earth.
Right.
Their down is completely opposite.
Right.
What's down for one is up for the other.
Yeah, yeah.
And it highlights a really fundamental point. Down isn't some fixed direction in space.
Right.
It's relative to your position and the gravitational forces that are acting on you.
Okay, so already down is like more slippery than we might assume. And to make things even more confusing, we throw around these words like gravity and weight and mass. Are those all the same thing?
That's a crucial distinction to make. We often use these terms interchangeably,
Right.
but they have very different meanings.
Right.
Weight, for example,
Yeah.
is the force of attraction between you and the Earth due to gravity. And it changes depending on where you are.
So, like, if I was on the moon, my weight would be way less.
Exactly.
Even though I'm still made up of the same amount of, like, stuff.
Exactly. Your mass, the amount of matter that you're made of, stays the same.
Right.
But your weight, the force pulling you down, changes depending on the gravitational field you're in.
Okay.
It's why those bathroom scales can be so misleading.
Oh, yeah.
They're actually measuring force, but they display it as mass based on Earth's gravity.
So the scale is basically making an assumption about where you are and giving you, like, a convenient shortcut that isn't the whole truth.
Yeah.
Speaking of which, Michael Stevens throws out this fact that just, like, blew my mind.
Okay.
He says that the Earth weighs 180 pounds on you two.
Oh, wow.
What is that all about?
It's a fantastic illustration of the principle of mutual attraction.
Okay.
Gravity isn't just about the Earth pulling on you.
Okay.
You're also pulling on the Earth with the same force.
Whoa.
Every object with mass exerts a gravitational pull on every other object with mass.
Wait, so if I'm pulling on the Earth, why doesn't it, like, move towards me when I jump?
Because of that mass difference again.
Okay.
The Earth is so massive compared to you that its movement is almost imperceptible.
Okay.
You know, imagine a tiny flea jumping on a giant elephant.
Yeah.
The elephant might feel a slight tickle,
Yeah.
but it's not going to move much, is it?
Oh, okay, I get it. It's like a cosmic tug of war.
Yeah.
Where I'm definitely the lightweight.
Right.
But this whole idea of mutual attraction makes me think about astronauts, like, floating around in space.
Okay.
Are they truly weightless?
That's a common misconception.
Okay.
They're not weightless. They're in constant free fall.
Hmm.
They're falling towards the Earth, but they're moving so fast horizontally that they keep missing it.
Yeah.
Essentially falling around the planet.
So they're always falling, but never, like, hitting the ground?
Right.
Okay.
Yeah.
That makes sense.
Yeah.
But if they're still subject to the Earth's gravity, wouldn't they eventually, like, slow down?
That's where the precise balance of speed and altitude comes in.
Okay.
At the altitude of the International Space Station, for example,
Yeah.
they experience about 90% of Earth's gravity.
Wow.
But their speed keeps them in this perpetual state of free fall. It's like a perfectly choreographed dance between gravity and motion.
This makes me wonder, like, what are the long-term effects
Right.
of that constant free fall on the human body?
Yeah.
I mean, their muscles and bones aren't working against gravity
Right.
the same way they do on Earth.
That's a question scientists are constantly studying. We know long-duration spaceflight leads to bone and muscle loss, changes in cardiovascular function, and even shifts in the immune system.
Wow.
Understanding how the body adapts to weightlessness and how to mitigate those effects is crucial for future long-duration missions to Mars and beyond.
That's amazing.
Yeah.
So there are all these implications for space travel tied to something as simple as down.
Exactly.
But back to our deep dive here.
Okay.
Michael Stevens argues that down isn't even a constant vector.
Right.
It's always shifting.
It is.
Why is that?
Because unlike those simplified diagrams we see, the Earth isn't a perfectly uniform sphere.
Okay.
It has mountains and oceans.
Right.
And variations in density. And even its rotation creates a bulge at the equator.
So all those variations in the Earth's mass mean that down changes slightly depending on where you are.
Exactly. The strength and direction of gravity vary subtly across the globe.
Really?
In fact, scientists use these tiny gravity variations to map the seafloor.
Wow.
Locate underground mineral deposits, and even find hidden chambers in ancient structures.
So down is more like a messy, dynamic force field?
That's a great way to put it.
Than like a straight line pointing to the center of the Earth.
It's this complex interplay of factors that's constantly in flux.
Okay.
And it gets even more mind-blowing when you bring in Einstein and his theory of general relativity.
All right.
But I think we should save that for part 2.
Okay, cliffhanger. I can't wait to hear how Einstein throws a wrench into everything we thought we knew about gravity and Pete.
Oh, down.
It's going to be good.
Yeah. Listeners, make sure to tune in to part 2.
Yeah.
And we'll delve into the mind-bending world of space-time and see how it changes everything.
Yeah.
I'm excited.
Me too. All right, so are you ready to have your mind blown?
I think so.
Because where we left off,
we were talking about how down is actually this constantly shifting thing, right?
Yeah.
Thanks to all the Earth quirks.
Right.
But then Einstein comes along and says, hold on, you're thinking about gravity all wrong.
Yeah. Yeah. That's where I started to feel like my brain might melt a little.
Yeah.
But I'm game. So what was Einstein's problem with the way we understood gravity before?
Right.
It seemed to work pretty well, explaining why things fall and planets orbit and all that.
It did work well.
Yeah.
For most everyday situations.
Okay.
But there were some things that Newton's theory couldn't quite explain. One big one was why objects of different masses fall at the same rate.
Okay.
Logically,
you'd
think a heavier object being pulled with more force would fall faster.
Right.
But that's not what happens.
Right, like that classic feather and hammer experiment.
Exactly.
In a vacuum, they fall at the same speed. That was in the Vsauce video, too.
Yeah, it's a classic demonstration.
So how did Newton account for that?
He said essentially that more massive objects experience a stronger pull.
Right.
But they also have more resistance to change in motion. It balances out.
Okay.
But Einstein's explanation was totally different, and it came from his famous equivalence principle.
Okay, equivalence principle.
Yes.
That sounds intimidating.
I know.
Break it down for me.
Okay, so imagine you're in a windowless room.
Okay.
You can't see outside.
All right.
Now imagine that room is accelerating upwards really fast.
Okay.
What would happen to everything inside?
I guess everything would get, like, pushed to the floor, right?
Exactly.
Like if you were in an elevator that suddenly shot up.
You'd feel pressed down.
Right.
But here's the key.
Okay.
You wouldn't be able to tell if you were being pulled down by gravity or if the room was just accelerating upwards.
Whoa.
That's the equivalence principle.
Okay.
Free fall feels the same as zero gravity.
So is Einstein saying gravity isn't even a force at all?
That's the radical idea.
Whoa.
He said what we experience as gravity is actually the curvature of something called space-time.
Space-time?
Yes.
I feel like I've heard that before.
Right.
But I'm not sure I really get it.
It's basically the combination of the 3 dimensions of space, up, down, left, right, forward, backward, and the dimension of time, all woven together.
So it's like the fabric of reality, the stage where everything happens.
Perfect analogy.
Okay.
Now, to understand how mass and gravity fit in, picture a stretched out rubber sheet. That's your space-time. Now put a bowling ball in the middle.
Got it.
It's going to make a dip, right?
Yeah.
Like a heavy object would warp the sheet.
Right.
Exactly. That's what massive objects do to space-time. They create a curvature.
Okay.
Now imagine rolling a marble across that sheet.
Okay.
It won't go in a straight line.
Right.
It'll curve inward towards the bowling ball.
Okay.
Following the dip.
Wait, so is that what's happening to us?
Yes.
We're not being pulled down by Earth.
Right.
We're sliding along the curve in space-time that the Earth's mass creates.
That's the idea.
Whoa, okay.
And here's the even wilder part.
Okay.
This warping doesn't just affect space.
Okay.
It affects time, too.
Hold up, you're saying time itself is getting bent out of shape?
Yep.
What?
Einstein realized that time flows slower in areas of stronger gravitational pull.
Okay.
So closer to a massive object, time actually moves a tiny bit slower than it does farther away.
Okay, my head is officially spinning now.
I know, right?
So down the direction things fall is the direction of slower time.
You got it.
Ooh.
It's not just a spatial direction.
Okay.
It's a temporal one, too.
Okay.
And this has some pretty crazy implications.
Like what? Give me an example, because I'm having trouble wrapping my head around this.
Well, think about GPS satellites.
Okay.
They're farther from Earth's gravity.
Right.
So time flows a tiny bit faster for them than it does for us down here.
Right.
If we didn't account for that difference, our GPS systems would be totally inaccurate.
Whoa. So this isn't just some like theoretical physics mumbo jumbo.
Yeah.
This has like real world applications.
Absolutely.
Wow.
General relativity is woven into the technology we use every day. But even on a personal level, it changes how we think about our place in the universe. We're not just in space and time.
Right.
We're part of this dynamic, interconnected fabric that's constantly being shaped by mass and gravity.
It's like realizing the stage isn't just a stage.
Right.
It's an active participant in the play.
Yeah.
But, okay, we got to come back to this down thing.
All right.
If it's the direction of slower time, does that mean time is flowing differently throughout my own body?
Yeah.
My feet are closer to the earth than my head.
That's a question that really takes us to the edge of what we understand about physics and biology.
Yeah.
The time difference is incredibly small.
Okay.
But it is there. And it makes you wonder about the implications for how our bodies function, how we age, even the very nature of consciousness.
Okay. That is a thought I'm going to be chewing on for a while.
Right. It's a big one.
It's amazing how what seemed like a simple question about down has led us to some truly profound mysteries.
It's a perfect example of how scientific curiosity can lead us down unexpected paths and open up whole new ways of seeing the world.
So what do you think? Should we try to tackle some of these bigger questions about time and consciousness?
Ooh, that's a good one.
Or are our brains sufficiently warped for one episode?
I think our brains are sufficiently warped.
Okay.
But I would love to tackle those questions another time.
All right. I think we've definitely stretched our brains enough for one deep dive. But it's so cool how like something as everyday as down can lead us to these mind-boggling concepts about the universe.
It really highlights how much we take for granted.
Right.
I mean, we experience gravity constantly. But how often do we stop and think about what it actually is?
Right. It's like we're swimming in this ocean of space-time. But we're so used to it that we barely notice the currents.
And those currents, those warps and curves, they're telling us something profound about the nature of reality itself.
So if we were to step back and try to like sum up all the wild things that we've learned about down today, what would be the key takeaways?
Well, first we have to ditch this idea that down is some fixed, absolute direction.
Right.
It's all relative to your position and the gravitational forces at play.
One person's down as another person's up.
Exactly.
Right.
And second, gravity, the thing that makes down feel so real, is far more complex than a simple attraction between objects.
Okay.
It's the curvature of space-time itself.
Right.
A bending of the fabric of reality caused by mass.
And that curvature means time itself flows differently depending on where you are.
Exactly.
Closer to a massive object, time slows down a bit.
Which leads us to that crazy notion that even within our own bodies, time might be flowing a slightly different rate.
Yeah, that's a thought I'm still processing. It's like, whoa, hold on. What does that even mean for how we experience the world?
It's a question that scientists are still grappling with.
Right.
But even without those deeper implications, I think we've gained a whole new appreciation for something we usually don't even think twice about.
we've gone from things fall down to down is the direction of slower time.
That's a pretty big leap.
Yeah, all thanks to a little curiosity and a deep dive into some awesome physics.
Absolutely.
And who knows? Maybe this will spark even more questions for our listeners.
I hope so.
Yeah. What other hidden complexities are lurking in the everyday world, just waiting to be uncovered?
Exactly.
So next time you drop something, or you trip over a curb, or just like feel the weight of your body against the chair. Remember you're experiencing the curvature of space-time itself.
It's pretty amazing.
It's pretty mind-blowing when you think about it.
It really is.
Well, dear listener, thanks for joining us on this deep dive into down.
Yeah. Thanks for listening.
We hope it's left you with a sense of wonder.
Yes.
And maybe even a little bit of vertigo.
A little bit of dizziness.
Yeah.
Yeah.
Until next time, keep exploring.
Keep asking questions.
Keep questioning.
Yes.
And keep looking deeper into the world around you.
There's so much to discover out there.
You never know what amazing things you might discover.
Exactly.